See, Biot Savart Law is used to find magnetic field due to a current carrying conductor. If you have a current, you can find out the magnetic field. The magnetic field due to this ideal length of conductor at point P. So this is R vector. R is a vector from current element to point P. So magnetic field due to this current element is given by, this is mu naught upon 4 pi ideal cross R upon R cube. See, the direction of dl always lie in direction of I. If I is flowing in this direction, this is going to be a direction of dl, right? dl is the current element, so direction of dl lies in direction of I, right? So this is your dB. dB is due to this dl length at point P is given by mu naught upon 4 pi I dl cross R upon R cube, where R is a vector from the current element dl to point P. Alright, R is a vector from current element dl to point P. Now suppose this is a current carrying conductor, and if I want to find out, see, before that I'll tell you two more forms of Biot Savart Law. See, this ideal can be written as, this current element ideal, I can be written as NEAV. I is NEAV, V is the net velocity. Or before that I can also write this as ideal, as I can be written as JA DL. A is the area of cross section. So this can be written as, say, DL lies in direction of I, J also lies in direction of I. So this JDL can be written as, since both J and DL lie in direction of I can write like this. JDL vector can be written as J vector DL. Direction of this is also along I, direction of this is also along I. So I can write it as J, this is ADL, or you can say J vector ADL. So this is written as ADL is d tau, this volume. So this is J d tau. Now J can be written as NEV, where V is the net velocity. What is N? N is the concentration of electron, number of electron per unit volume. So N into d tau is the total number of electron in the volume d tau, and into E is the amount of charge per unit volumes. This is written as dq, or we write it as VdQ. So you please remember, IDL equals to VdQ is equal to J d tau, right? Remember this. So in this way you have two more expression of Biot Savart Law, that is mu naught upon 4 pi I can write J cross R d tau upon R cube. This is mu naught upon 4 pi V cross R dq. There are three expressions of the Biot Savart Law. Now we will see the application of this Biot Savart Law for different cases. We will find out the electric field due to different type of current distribution, right, using Biot Savart Law. Let's find it out first for the short conductor. Let us take a short conductor of finite length, and find the Biot Savart Law in the vicinity of that conductor using Biot Savart Law. So let's try to do that. Suppose you have this short conductor, and we have to find out the magnetic field at this point P. You have to find out what is the magnetic field at point P due to this short conductor. So this is short conductor. Suppose the length of conductor is defined by the angles. So this is, let's say 1 end makes an angle alpha with the horizontal, other end is denoted by beta. Now let us take a current element over here. Let's take a current element, right? This is IDL. Suppose I is the current flowing through it. This is I have taken DL length of conductor, right? So this is your R vector, right? This is your R vector. Let's suppose this angle is theta. This angle is theta. So if I write this as L and this is as DL, then what is the L? L is D tan theta. This is a length L. This is length L, right? So your DL will be written as d sec square theta d theta. So your dB can be written as, from Biot Savart law, mu I dl cross R on 4 pi R cube. So this is nothing but mu naught upon mu naught I 4 pi. What is dl? dl is R is what? What is R? I write it first as dl into R. dl into R. And what is this angle? This is 90. This is theta. This is 90 plus theta. Sine 90 plus theta upon R cube. So your R can also be written as d sec theta, right? So the magnitude of dB, that is dB, will be written as mu naught I upon 4 pi. I can just put dl also, this R and R, so it will become R square. So d can be written as d sec square theta d theta. Sin 90 plus theta is cos theta. So R square is what? D square sec square theta. Mu naught upon 4 pi d. This becomes cos theta d theta. So the magnitude of B can be written as integral of t. Can you tell me what is the direction of, I write it, this is cos theta d theta. Can you tell me the direction of B? See, you can use Biot Savart law. See, this direction will be, see, dl lies in this direction, R lies in this direction. If you want to find direction of dl cross R, you put the fingers of right hand. You put the fingers of right hand in direction of dl like this. See, you put the fingers of right hand dl in this direction and curl it towards R. Don't put the finger like this. You can't curl it in this direction. So you put the fingers like this in direction of dl, right? And you curl it towards R. Curl it towards R, right? There is a finger in dl direction and curl it towards R. The thumb gives you direction. See if you can see the figure, right? Yes, thumb gives you direction over here, right? So put the fingers of D this direction. Thumb will go inward, right? Thumb will go inward. So this is right. So put the fingers of right hand in the direction of DL. Curl your finger towards R. The thumb gives you direction of DL cross R. The thumb will give you direction of DL cross R, right? So the magnetic field to this current element lies in inward direction. The magnetic field will lie in inward direction, right? Now you just see, here you are integrating. So for every element, magnetic field will go in inward direction. So I am integrating in that way. If you take element anywhere, the magnetic field will lie in inward direction. So this can be integrated like a scalar. The magnetic field for all the element can be added up. So I am adding it up to an integration. Now what is the limit of theta? So So whenever you want to find the limit of theta, you choose a line, certain line as reference. See, initial line, you have taken a reference for measuring theta. I have taken this to be theta. So this is the reference. Reference is always taken as theta equals 0. So your reference begins from theta equals 0 to theta equals to alpha. If on this side you take it as positive, then on this side you have to take it as negative. So it is beginning from, this will be direction theta equals to minus beta. It is increasing to theta equals to 0 and then to alpha. So theta is beginning from theta equal to minus beta to theta equals to 0 to theta equals to alpha. This is theta equals to alpha. So it is varying from minus beta to alpha. This is 4 pi d. This is sine theta and minus beta to alpha. Sine alpha plus sine beta. This is how we can find out the magnetic field to a short conductor. It will lie in inward direction. You can use thumb rule also. Put your fingers in the direction of current. The curl of fingers will give you direction of magnetic field. Put your fingers in the direction of current and curl your fingers. The curl of finger will give you direction of magnetic field. So if you put your fingers, right hand, thumb of your right hand, put the thumb of your right hand in the direction of I, the fingers will give you the direction of magnetic field. So if I put my thumb like this, right, and the fingers will give you the direction of magnetic field inward direction, right. So anyway, you find the direction either by DL cross R or you find it by right hand thumb rule. It will give you inward direction, right. Now if the conductor is infinite, for infinite conductor, what will happen to alpha and beta if it goes to infinity? This alpha will go on increasing. At infinite length, this alpha and beta will go on increasing. For infinite conductor, this alpha and beta will become equal to pi by 2, and hence your B is V naught I by 2 pi d, right. For semi-infinite conductor, see, you take your one end point like this. See, this is a semi-infinite conductor. One end is defined. You have to find out, say, magnetic field at point P. This is semi-infinite. This is one direction. It goes to infinity. It starts from here. So for semi-infinite conductor, your beta will be 0, but alpha is pi by 2. So your B is mu naught upon 4 pi d. Alright. So this is how we can find the magnetic field due to a short conductor at any point P in the vicinity using